Hello, everyone. Welcome to the World Statistics Society workshop, Random Graphs and Dynamics. So this workshop is organized by the Applied Probability section. The section organizes conferences all throughout the years. And if you want to hear of future meetings, be sure to subscribe to our mailing list, Applied Prob GXML. So I just type in the chat box the way to subscribe to this mailing list. Now, before we start the meeting, let me just remind you that this event is being recorded. So if you do not want yourself to be recorded, please make sure you turn off your camera. And can I ask everyone to mute yourself unless you're the speaker? Okay. Now, without further ado, let me introduce our first speaker of the day. So it's a huge pleasure to have Peter Mörters from the University of Cologne. So he's going to talk about the contact process on evolving networks from fast to slow dynamics. During Peter's talk, feel free to ask your questions. You can either raise a hand or type your questions in the chat box. Now, over to you, Peter.
Thank you very much for the nice introduction. I hope you can all hear me and see my slides. Okay, right. Okay, so the topic of the talk is the contact process on evolving networks. And the plan is to have the evolution of the networks go from fast to slow dynamics. So we will vary the dynamics of the evolving networks and keep the dynamics of the contact process constant. What I'm going to talk about is joint work with Emmanuel Jacob from École Normale Supérieure in Lyon and Amitai Linker from the University of Cologne. And the work is split into two halves. One half is a paper that we published already in 2017, and the other half is still in progress. So there are some new things and some old things in there. Okay, so the aim of this project is to understand how processes on large complex networks can be affected by time variability of the network. And of course, this is a huge topic, and we look at a very, very modest bit of it, namely results for the contact process on scale-free networks. So let me begin by saying what the contact process is. So this is a model for the spread of an infection, in our cases, on a finite graph. So all the graphs that I'm looking at are finite graphs. And I'll let an infection spread on this graph. So every vertex can be either infected or healthy. And infected vertices infect their neighbors in the graph at a fixed rate lambda. So if you're a healthy vertex, you get infections with the rate given by lambda times the number of your infected neighbors. And infected vertices can recover, and this happens at a fixed rate, which we set to 1. So one of the rates we can set to 1, and it's the recovery rate. So the lambda, the infection rate, is the only parameter there. And once recovered, a vertex is again susceptible to infection by its neighbors. So in the epidemiology literature, this is called the SIS model, because every individual, every vertex is either susceptible or infected, and after infection, it can return to the state of being susceptible. Because this happens on a finite graph, and any two states can communicate with each other in this Markovian structure, except for the state that everyone is healthy, which is an absorbing state that you never leave. The process is going to end up after some random extinction time t in the state that everyone is healthy. So we always look at this from the point of view of the infection. Extinction is extinction of the infection. And once extinction has happened, there is no comeback, and everyone stays healthy forever. So our plan is to look at the situation where the infection has broken out. So we start the process with all vertices infected, and the question is, how large is the extinction time? And in the situation that we are, there are two possible scenarios. One is what we call fast extinction, and that means that for a sufficiently small infection rate lambda, so lambda positive but smaller than the critical lambda c, the expected extinction time is at most polynomial in the number n of vertices in our finite graph. And the other scenario is a slow extinction, and that means no matter how small the infection rate, with high probability, so with probability going to 1, the extinction time is at least exponential in the number n of vertices. So as n goes to infinity, the probability that the extinction time is bigger than some deterministic exponential sequence goes to 1. Okay, and these are of course not complementary events, but it turns out that in all the situations that we look at, either of these two situations holds. So fast extinction is an event that holds for sufficiently small infection rates, and slow extinction means no matter how small the infection rate lambda is, we have a very large extinction time. Okay, so the situation is, we ask whether we have fast or slow extinction in these situations. Okay, so this is all about a finite graph, and now I have to tell you what graphs I'm looking at, or more precisely, what graph sequences, because we want to look at evolving or dynamical graphs. Okay, so I'm now speaking about the network dynamics. So we have a parameter gamma, which is important. It's a number between 0 and 1. And that's the parameter that's responsible for the scale-free nature of our network. There's a parameter beta, which is positive, which tells us something about the edge density in the graph, and that's not very important. And then we have a kappa, which is the update rate. So that sort of tells us the dynamics of the network. And the vertex set of the graph is always, it's a finite graph, so it has capital N vertices. That's not changing, and the vertices are always numbered from 1 to n. And small indices indicate large strength of powerful nodes. So vertex number 1 is a very powerful vertex. Number 2, 3, and so on are still very powerful vertices. And the not so powerful vertices have indices that are of order n, essentially. Okay, and this graph is evolving by a rule which we call vertex updating. So we have a sequence gt evolving in continuous time, and at every time t, the graph in this graph sequence is the graph with the vertex set given by the vertices numbered 1 to n and some edge structure. Okay, and I tell you the Markovian dynamics of this sequence. So every vertex I has an independent clock which strikes after an exponential time, and the rate at which these exponential this exponential time is the kappa of I. So this kappa that I've introduced at the top of the slide, kappa of I is the rate at which the ith vertex updates. And when this clock strikes, the vertex updates, which means that it forgets all the neighbors that it had and builds a new neighborhood. So all adjacent edges are removed and new edges are formed. And And so I is the vertex which is updating, and it forms an edge connecting it to a vertex j with the probability which I call Pij. And this happens independently for every other vertex j in the network. And the probability, this Pij, is here given by n over I to the gamma. So that is actually the up to constant, the expected degree of the vertex I, n over j to the gamma is the expected degree of the vertex j. So it's the product of the expected degrees of the vertex divided by n and multiplied with this unimportant constant. Because this could formally be bigger than 1, I take the minimum with 1. Okay, so that's the rule for our graph sequence, and what we are looking at is the stationary graph process under this dynamics. So stationarity then tells us that in the stationary state there is an edge between vertex I and vertex j with probability Pij. Okay. And that's the graph dynamics. So it's important that the dynamics we're looking at is a stationary dynamic. So it's not that we add vertices to the network as you often see in models, but the network is sort of this fixed population, fixed large population, and what changes is just the edge structure between the vertices. And what does not change is the power of the individual vertices. So vertex number 1 will always remain the most powerful one. There are lots of choices here in this model, and one of the choices is the vertex updating rule. So so this means that when every vertex has a clock and it changes its entire neighborhood when the clock rings. An alternative to this would be edge updating, where you give every unordered pair of vertices a clock, and when this rings, you decide whether the edge between I and j is present or not. Our methods allow to study both of these updating rules, vertex updating and edge updating. But the results are more interesting for the vertex updating case, so in this talk I'm going to tell you only about the vertex updating rule. And the other choice that we've made is these this connection probability between vertex I and j, which is proportional to the expected degrees of vertex I and vertex j, and that's sort of the crucial thing here is this factor structure. So there is this function of I multiplied with the function of j. So that's these kind of structures you see in many models of scale-free networks, like in the configuration model, or this actually is an instance of the Chang-Lu model. Lots of models work like this, but there are alternatives. So, for example, we could also deal with Pij, where for the larger value of j, you take n over j to the power 1 minus gamma, and for the smaller value of I and j, you take n over I to the power gamma. So you take different powers here depending on which of I and j is bigger. And that would sort of be reminiscent of the structure of a preferential attachment network. Again, our proof techniques allow to deal with this situation, but I've made the choice of looking at this kernel because it's has a particularly rich phenomenology, which is what I'm after. I want to see the phenomena that can arise in this situation when I let this process run on this dynamical network. Okay, but what's in common with in all these things is it's a stationary graph process, and at every time t, the graph is a scale-free graph in the sense that if I look at the proportion of vertices of degree k, as n goes to infinity, this converges in probability to some number mu of k, and when then in turn k is very large, this mu of k behaves like decays like k to the minus tau plus some error a little over 1. So the degree the degree of a typical vertex decays like k to the minus tau, and this power law exponent tau is explicitly given in terms of the model parameter gamma as tau equals 1 plus 1 over gamma. Okay, so gamma is the parameter that I put in, but it's a direct translation of this power law exponent tau, which is 1 plus 1 over gamma. I'm not sure whether you can see my highlighting here. Can you?
Yeah, we can see it.
Okay, thank you. Just for a second, I thought I was on my own. Good, right. Okay, so this is a straight translation, and when gamma varies from 0 to 1, tau moves from infinity to 2. So this power law exponent is always a number tau bigger than 2. With 2 being sort of the most inhomogeneous graphs that you can have. And I will formulate all our results in terms of this tau for better comparability, because you might have your favorite random graph model or scale-free graph model, and you know that this power law exponent tau is an important order parameter. So, for example, when you look at the neighborhood of a typical vertex in your graph, when tau is between 2 and 3, and you look at the neighbors of the vertex and the neighbors of the neighbors of the vertex and so on, this looks like a super exponentially growing tree when tau is between 2 and 3. So there's a very high conjectivity there. And when tau is bigger than 3, then you have just an exponentially growing tree. So there is a sort of standard result for all these models that says when tau equals 3, you have a transition in the graph topology. And of course, we're sure that this will have some influence on the contact process, which we are now running on this dynamical network structure. So we now look at the Markovian structure that you get when you have the contact process dynamics running at the same time as the graph dynamics on this on this structure. And this is, of course, still a Markovian process. Maybe after I advertised our work and said that we're very flexible with respect to these kernels with our methods, and also flexible with respect to the updating rules, I should say that we're not flexible with respect to one thing that's built into this model, and this is the independence of the evolution of the graph and of the infection. So in the very interesting case that the graph adapts to the infection behavior, then the methods of our proofs essentially all collapse. Okay, but for the time being, we look at the situation of independent dynamics of the graph and of the infection. Okay, let me just remind you of the boundary cases. So the boundary cases are very slow or very fast evolution. So the slowest evolution, the slowest network dynamic that you could have is that there is no change at all. So then when this update rate kappa goes to 0, or in other words, when there is no updating, and if there's no updating and we just have the stationary graph, in this case, for all values of tau, and all values of tau are bigger than 2, so for all tau bigger than 2, the contact process has slow extinction. Okay, and that's a result. And One of the first instances is the work of Chatterjee and Laurent from 2009, but a few people knew that before, and you can find it if you look very closely in a couple of papers before that. The Chatterjee and Laurent results a little bit weaker than what I've formulated as slow extinction and and it's definitely in Mountford-Wallerstein and Yao from 2013, where it's rigorously proved that in this case there is slow extinction. Okay, so that's the slowest dynamic. You always have slow extinction here, so you always have survival of the infection for a very long time on this complex networks. The other situation is very fast dynamics. If we let the update rate go to infinity, in this case, you could assume that whenever the infection wants to use an edge to infect a neighbor, this edge is newly sampled compared to the last use of this edge. In other words, you're on the complete graph, and the infection rate is lambda times Pij. So lambda is the infection rate on the graph, and Pij is the probability that the edge is there. So you could just assume that whenever an infection happens, it happens with the rate whenever the infection wants to pass on. Is passed on an edge ij, this happens with probability lambda times Pij. So this is the mean field model, and it's been shown that for this mean field model, there is a slow extinction for tau less than 3. So for this very well connected situation, but for tau bigger than 3, there is fast extinction. Okay, so there are small infection rates where the infection cannot sustain itself for a long time. And that's been in the physics literature for 20 years now, for example, by Pastor Sartoris and Vespignani in 2001. So what you see is that in these two boundary cases, you have different behavior. For the case of the static network, no updating, you always see slow extinction. And for the case of very fast dynamics, this mean field model, you have a transition at tau equals 3, where this is also the point where the network, where the graph topology changes, and you have slow extinction only when tau is less than 3. So the natural question that we are going to ask is whether we can interpolate between these two boundary cases. And we do this by looking at update rates, and these update rates in our situation are allowed to depend on the rank of the vertex or the expected degree, which is the same thing. So there is a new parameter which is called eta, which is a real number, can be negative or positive, and we take n over I to the gamma, which is the expected degree of the ith vertex, raise it to the power eta, and multiply it with some fixed constant kappa, and this is the update rate of the vertex. So interesting and easiest case is when eta is equal to 0, then this is all constant, and then every vertex updates with a constant rate. Okay, this is the situation where the dynamics of the contact process and the dynamics on the networks are on the same scale. Okay, so this is a situation which we definitely in which we're definitely interested in, and we will see that we see some behavior which is in between our two boundary cases in this situation, but we want to see a full interpolation that allows us to move towards the boundary cases, and that's why we have this parameter eta, and so the update rate is in this case given by the expected degree of the vertex to the power eta. So for positive eta, the powerful vertices update very fast, and for negative eta, the powerful vertices update very slowly. Okay, so there is it will turn out that this choice will allow us to to zoom into this window where things are happening between the slow and the fast dynamics. Okay, if you don't do this degree dependence of the update rates, if you just say, oh, I multiply my update rate with n, then you will just or with n to some with n to the eta, say if eta is positive, you will just go to the very fast dynamic. And if eta is negative, you will just go to the slow dynamics, and you won't zoom into this into the range where things are happening smoothly in between, or where you interpolate between the boundary cases. So this is the justification for these rank-dependent update rates, is that this indeed will allow us to zoom into this window where we have the transition between the boundary cases. Okay, so important, eta, the parameter eta, determines the speed of the network evolution. Eta equals 0 is network evolution, and the evolution of the contact process are on the same scale. Eta bigger than 0 means network evolution is faster, and eta less than 0 means network evolution is slower. Okay, so I think I've said everything about the model, and unless somebody stops me by asking a question, I will move on to the results. Okay, so here is the first result. Results about eta bigger or equal 0 are from 2017. The results about eta less than 0 are new or in progress, actually. So here's the result. So we consider the contact process on our evolving network, and we have fast extinction if either eta bigger or equal a half, fast evolution, and tau is bigger than 3, or if eta is positive or non-negative but less than a half, and tau is bigger than 4 minus 2 eta, or eta is negative and tau is bigger than 4 minus eta. And we have slow extinction. This is maybe the more interesting part. If these inequalities for the tau here are reversed with strictly less rather than strictly bigger. In this case, there's slow extinction, and there is a picture that shows this. So in this picture, on this vertical axis, there is eta, which goes over all of R, and on the horizontal axis, there's tau, our power law exponents, which goes from 2 to infinity. So what you can see is when eta is bigger or equal than a half, then the transition between the slow extinction and the fast extinction case happens when tau is equal 3, that is when you actually expect it, because the topology of the network changes. And then when eta is between 0 and a half, it moves from 3 to 4, and when eta is negative, it goes further to this transition line goes to infinity in tau. But there are 2 points where where the structure of the changes. So here, when we move from the vertical line to this slope, and at eta equals 0, there is another change in the slope here. And when eta goes to minus infinity, we are looking at this the slowest possible situation, so the static case, when we always have slow extinction. So this picture really interpolates between the two situations known, but there are interesting things happening at eta equal at this point here. I'm not sure whether you see my cursor, but at this point when tau is equal to 3 and eta equals a half, and when tau is equal to 4 and eta equals 0. And I'm going to explain in a minute what happens there. Okay, again, so this picture interpolates between the mean field case that you see at as eta goes to infinity, so right at the top of the picture, and the static case when eta goes to minus infinity at the bottom of the picture. the transition between slow and fast extinction can happen at any tau bigger or equal 3, depending on the speed of the network evolution. And the mean field behavior happens as soon as eta is bigger or equal 1/2. So what I'm going to do now is I'm going to give you the heuristics for this theorem, which is also which can be turned into the proof of the slow extinction of the existence of the slow extinction phase. Okay, and at the end of the talk, if I have time, I'm going to say something about fast extinction, but let me at this point make clear what the heuristics is behind this theorem. So I'm going to explain heuristically how slow extinction works when eta is bigger or equal 0 and tau is bigger than 3. So let me just go back. So when that slow extinction works for tau less than 3 is somewhat unsurprising, because in this case the network is highly connected, and it's clear that it's a very good environment for our infection, and therefore we have long survival of the infection. What's more surprising is that this is also possible when tau is bigger than 3 and the network doesn't have this extremely connected structure. So I'm going to show how a slow extinction works when eta is bigger or equal 0 and tau is bigger than 3. I explain why we have the mean field behavior as soon as eta is bigger than 1/2, or actually bigger or equal 1/2. And I'm going to explain what happens when eta is negative and when we're in the slow regime. What changes there? Okay, so our heuristics is based on the fact that the infection is maintained on a set of vertices that are very powerful. And in our setup, very powerful means low index. So the crucial quantity is some A, depending on the infection rate lambda, in such a way that A of lambda goes to 0, and the vertices with index between 1, 2, and up to A of lambda times n are the very powerful vertices on which we can maintain the infection. And these vertices we are going to call stars. Okay, so stars are very powerful vertices that we can recognize by having an index less or equal A of lambda times n. They typically have a degree. You remember the degree was n over I to the gamma typically, so the typical degree of a star is A of lambda to the minus gamma. So that's large because A of lambda goes to 0 and gamma is between 0 and 1. The infection it will survive on these stars. And crucial for the survival when tau is bigger than 3 is that there is a local survival mechanism. And how this local survival mechanism works is the following thing. We take an infected vertex of high degree K, and at the time when this vertex recovers, so it recovers with rate 1, but when it recovers, it's typically embedded in a sea of infected neighbors. And how many infected neighbors do we have? Well, if the degree is K, we have K neighbors in total. This kappa times k to the eta is the update rate, so 1 over kappa to the k times eta is the time that this vertex is already a neighbor, and through all this time the infection is passed on with the rate lambda. So typically you have this many infected neighbors. The probability that if you recover and you have this many infected neighbors, that you're not immediately reinfected by these neighbors is given by the competition between clocks. And there is one clock which is the update clock, which has rate kappa times k to the eta. And if this update clock rings first after the recovery, then the infected neighbors have not had the time to reinfect you. But this is rather rare. In fact, the rule is that one of the infected neighbors will immediately reinfect you. So the probability, and there are and this is the number of infected neighbors, and each of one reinfects you with rate lambda. So the probability of no reinfection at recovery is given by the rate of the recovery clock divided by the sum of the rates of all the clocks, which is this term. And if forgetting this constant kappa, you see that this goes like k to the 2 eta, if I take this k of eta to the eta from the denominator, so this goes like k to the 2 eta divided by k to the 2 eta plus lambda squared k, and that's small if lambda squared k is much bigger than k to the 2 eta. And in this case, the infection stays alive for time units. It's 1 over the asymptotics of this term, so lambda squared times k to the 1 minus 2 eta. So at this single vertex, this single star can survive for a longer time because most of the recoveries are not relevant because you get immediate reinfection from your neighbors, and in this way you can stay alive, or the infection can stay alive on this star alone for lambda squared times k to the 1 minus 2 eta time units. And this can be much bigger than 1, but only if eta is less than a half. If eta is bigger than a half, this local survival strategy gives you no advantage, and that means you see the mean field behavior. So this is the first heuristic thing that I've explained. You have the mean field behavior when eta is bigger or equal to a half, because this local survival strategy doesn't work in that situation because it extends, it can extend the survival of the infection at a single star for this many time units, and this should be bigger than 1 for this to be useful.
Sorry, Peter.
Yes?
This seems to be the question from the audience. Someone have raised their hand.
Okay.
I cannot read the name, but so would you like to unmute yourself and ask a question?
I think it might have been me and I did it by accident, sorry.
Oh, okay.
Okay, good. So I just briefly explain now when eta is non-negative but less than a half, how we can make use of this local survival strategy. So we want to sustain the infection on the stars, and here is a back of the envelope kind of calculation for when this is possible. So you look at, so this is the time scale. So I've now plugged in a to the minus gamma, which is the expected degree of a star. So this is the time the local survival strategy allows us to keep the infection at the star. And throughout this time, every star indicated x here in this integral, so x goes from 0 to a, can infect another star if there is a connection. So this is pxy is the probability of the connection, and it does this proportional to the infection rate lambda. Okay, and this should give us a proportion a again of infected vertices. So this is the left-hand side is sort of the average number of if you have a dense infection in the stars, this is the density of the infection after one cycle of recovery in this new time scale, and this should be of order A again, so it should be dense again. So if you plug this in, this is very easy. Okay, so this double integral is in fact what you get from the Riemann sum when you plug in the normal, our connection probability, and the pxy is x to the minus gamma, y to the minus gamma. If you integrate this, you have a to the 2 minus 2 gamma. So you put the lambdas together, it's lambda to the 3, a to the 2 minus 2 gamma 1, a from the right-hand side I put here. So it's 1 minus 2 gamma, another minus gamma is 1 minus 3 gamma plus 2 gamma eta. So if this is bigger than 1, then this strategy should work. And this can be, that's possible for very small lambda if the exponent of the a is negative. So if 1 minus 3 gamma plus 2 gamma eta is less than 0, and if you translate this to our tau, which is 1 plus 1 over gamma, it should be less than 4 minus 2 eta. So that's the criterion that we see in the picture for positive eta. Now, I've said when eta is negative, when we make the dynamics slower, things change again. So what changes when eta is less than 0? Well, when eta is less than 0, then the stars update very slowly. And at the same time, we have a lot, the infection can be held at the star for a very, very long time. But this heuristics here is based that throughout the time when we have the star infected, it passes on the infection to other stars. But because the stars now update very slowly, this is no longer correct. It will try to pass on the infection, but it will see the same stars all the time because the stars don't update. So in this heuristics here, there's the assumption of a certain mixing of the connections between the stars that's no longer satisfied when eta is less than 0. So when eta is less than 0, what may happen is that the time between updates of the stars exceeds the time of the transmission. So a to the gamma eta is the time between updates of the stars. 1 over lambda is the time of transition. If this is bigger, then we see a depletion effect in the sense that our strategy will not be as efficient in keeping the infection alive, because we will try to infect stars that are already infected, and we overcount with the previous argument. And indeed, this less effectiveness of the strategy means that it only works if eta is negative when tau is less than 4. Okay, so these arguments that will lead to a proof for slow extinction. For negative eta, this argument will only work when tau is less than 4, so to the left of this dotted line. However, we also have slow extinction when in this wedge here between this dotted line and this solid line. And the reason why we have this is because there is a different strategy for slow extinction that still works when tau is less than 4 minus eta. And the idea of this strategy is that instead of a star infecting directly another star, it will use intermediate vertices, which are not stars, that are not so powerful, but there are many of them, and it will infect one of these intermediate vertices, and the intermediate vertex will then infect the star. So the infection does not go from star to star directly, but via a connecting vertex. This is most of the time, or when eta is bigger than 0, this is an inferior strategy because you need 2 infections passed along the edges, so you have a factor lambda squared rather than lambda in your formula. But because the depletion effect that renders our old strategy less efficient is not there in this case, because we don't when eta is negative, we don't update the connecting vertices, the non-stars, as slowly as the stars. So they still update at a steady rate. There is still the mixing, and therefore this works. And Heuristics is as follows. So you have now you still have the strategy of local surviving. So a vertex of degree k at a recovery has now lambda times k infected neighbors. So it has k neighbors, and each one is infected with probability lambda, and the probability that there is no infection at recovery is again given by the update clock k to the eta, and lambda, the rate, times the number of infected neighbors. And this works if lambda squared k is bigger than k to the eta, and gives lambda squared times k to the 1 minus eta time units on which you have an infection alive at the star. And now we look at the connection via a connector. So two things change, or three things change in this formula. One is this local survival time, which is a little bit different there. Then this is a big disadvantage. We have lambda squared because we have to pass the infection along two edges rather than one. This was lambda before. And then we have the number of paths from x to y, which are now paths of length 2. So there is a pxz, pzy. So this z is the intermediate vertex. But this third change doesn't make any difference because the p is x to the minus gamma z to the minus gamma. So the middle integral is of constant order. And we have lambda to the 4 from these two lambda squares, and a to the 1 minus 2 gamma as before, and times a to the minus gamma times 1 minus eta, which gives us this term here. The exponent should be negative for this to work, which means that tau, which is 1 plus 1 over a gamma, must now be less than 4 minus eta for this strategy to work and give slow extinction. And it was 4 minus 2 eta before in the picture. Okay, so a summary here: when eta is negative, then we have the slow update leads to a depletion effect. Our old strategy was less useful, but we have an alternative strategy that still gives us slow extinction for values of tau bigger than 3, according to the picture that you see here. So this wedge here is also explained. So what you see from the heuristics is that there are different survival strategies working for our infection, and therefore it's the natural next question after seeing this picture is: can we say more about the different survival strategy? Can we sort of make the best survival strategy some more explicit in a theorem? And this is what happens now when we look at so-called metastable densities. So we would like to look closer at the survival strategies of the infection. These are metastability effects in the sense that that our Markov process stays in a metastable state, which is not the stable state, because the stable state would just be everyone healthy, but there is a metastable state in which it can stay for a very long time. And this state is sort of characterized by the proportion of infected vertices. So in the slow extinction case, we look at the expected proportion of infected vertices at time t, call that IN of t, and we look at times Tn that go to infinity in n, but slower than exponentially. So the limit as n goes to infinity of this proportion of infected vertices goes to some value rho of lambda positive, and this rho of lambda is the metastable density. Here is a simulation done by Lucas Simon. He's a student, and you can see what happens here. You start with everyone infected, so that on this axis is the proportion of infected vertices. You start at 1, you very quickly drop to some level, and then you fluctuate around this level. and you essentially stay there forever. Now this process dies out in finite time, so at some point you will hit the zero. The fluctuations there are not bounded in this sense. So at some point the fluctuations below will be such that you hit zero, but you see that it will not happen in your lifetime, and not in mine, and not in anyone's. It's just extremely unlikely to ever happen. And the level around these fluctuations, that's the metastable density. So that's what we would like to find out. Okay. And what we actually want to find out is how this metastable density rho of lambda looks like when lambda goes to zero. Okay, and when lambda goes to zero, this goes to zero like lambda to some positive exponent, and these exponents are called the metastability exponents, and we would like to find out what they are. And I've formulated as a theorem the result for the case eta is equal to zero. So this is the case, remember, when the contact process and the infection are on the same scale. So are variable on the same time scale. So in this case, the metastable density satisfies rho of lambda is lambda to the 2 tau minus 2 over 4 minus tau plus little o of 1, when tau is between 5½ and 4, and lambda with another exponent when tau is between 2 and 5½ Tau is always bigger than 2, and when tau is bigger than 4, we don't have slow extinction. So this shows that in the phase where we have slow extinction, there are two regimes for this metastable metastability exponent, and they characterize different strategies. Okay, and what we want to have and partially have is our results for these exponents that work for all tau and all possible values of eta. And in the next slide, I'm going to show you this very rich picture that emerges when you do this. So, okay, maybe I should say here first for this eta equals 0 case what the strategies are. So I said when tau is less than 3, the network is highly connected, and the infection can spread very easily on the network. So this is when tau is less than, and there's no need for a local survival strategy. And this is possible when tau is less than 3, but only when tau is less than 2.5. So when tau is less than 5½ this is also the best strategy. When tau is bigger than 5½ and less than 4, then the local survival strategy that I described is better, and better means that we can choose a larger set of stars on which the infection survives, and the larger set of stars gives us a higher density, a higher metastable density, because the density, the metastable density comes from the infected neighbors of the stars. So A of lambda is the density of the stars. A of lambda to the minus gamma is the degree of the stars. So A of lambda to the 1 minus gamma is the density of the neighbors of the stars, and lambda is the density of the infected neighbors of the stars. And this is a lower bound for the metastable density, and it turns out to be a very good lower bound in all our situations. So when we compare two strategies, we compare the A of lambda to see how big the set of stars is, and that gives us by this formula the metastable density. And this is, of course, first a lower bound that has to be turned into the upper bound later. Okay, so I'm going to talk to you for the next 5 minutes of the full picture, what happens, and just as a reminder, the upper half of the picture, the fast dynamics, when eta is bigger or equal 0, is in our 2017 papers, and the lower half is work in progress. We have the lower bounds, we have some upper bounds, and we have ideas for the other upper bounds, but it's not fully written up. Okay, so this is my picture. As before, tau is this the power law exponent going from 2 to infinity with very inhomogeneous networks on the left here. And eta is the parameter that tunes the speed of the network evolution. Eta equals 0 means they are on the contact process and network evolutions are on the same scale. Eta to infinity is the case of very fast dynamics, eta to minus infinity, very slow dynamics. The bold black lines are the phase transitions. So what do I mean by phase transitions? Now, for every point tau eta, there is a metastable exponent. Okay, so this is a function that this is the domain of a function that for every tau eta, for every pair, every point here, we have an exponent. And when this function that plots the exponent against tau and eta is not analytic, then we say it's there is a phase transition. And indeed, in this case, it's always continuous, but where the black lines are, it's not differentiable. So there's a first order phase transition. All these black lines, bold black lines, are phase transitions. Okay. The red lines are not phase transitions. I'm going to explain this in a minute. Okay, so when eta is bigger or equal to half, I said we see mean field behavior, and this means this blue phase is where we have fast extinction. So this happens when tau is bigger than 3 here, and when tau is less than 3, the quick direct spreading strategy that does not use any local survival strategy is best. And in fact, the only possibility here, and this is what happens, what we see when eta is bigger or equal to half. When eta is less than a half, the local survival strategy becomes possible, and we see this yellow phase emerging, which is when we have the local survival strategy and therefore a delayed spreading strategy here. So when eta becomes negative, this strategy is better than the also possible quick direct spreading until we hit 2.5, and then even for eta negative, the direct spreading is best. Whereas in this whole yellow region, the local survival combined with direct spreading from star to star is best. Now, why are these phase transitions within this region? Now, when we pass this, the line here, so this kite is where everything is where we have this delayed direct spreading, and the cost for the delayed direct spreading comes from the spreading from star to star. So we need to make the A smaller, the set of stars smaller in order to allow spreading. When we move into this parallelogram line here, the cost is exclusively from the local survival strategy. So we have to make A small to have local survival, and the direct and the spreading between stars is then the set of stars is already small enough so that the spreading works. In this triangle here, we see the depletion effect that I described. So when we pass this line here, we have to start taking into account that typical infections between stars will infect stars that are already infected, and therefore we have to reduce the efficiency of the strategy is reduced. So in this triangle phase, there is in this triangle here. There is delayed direct spreading is still the best strategy, although we have a depletion effect that makes it less efficient. When we cross this line here, we are in the situation that we have the local survival mechanism, and we don't pass the infection directly from star to star, but it's via a connecting vertex. And this is the green strategy. Within this green strategy, we have another phase transition here. This is when the cost of maintaining the local survival becomes is higher than the cost of doing the spreading, and therefore there's another discontinuity of the derivative in the local exponent. So there is this phase here, which has a strange shape. I'm not sure whether you see my cursor, but if you just follow these black lines that include this pink area and then a bit of the yellow and a bit of the green, this is one phase. This is the phase where we pay for the survival by just having the local survival. But in this phase, there is a crossover between different strategies. In the yellow bit, the strategy of spreading is directly between stars. In the green phase, it is using the connectors. And in the pink area, both of them are possible. Both of them happen simultaneously. We only pay for the local survival, and therefore there is no phase transition at these red lines, although the strategy changes. Okay, and so this picture, these heuristics that I explained to you now are you can turn them into lower bounds for the metastable densities, and for the upper bounds you need a more sophisticated approach, and it will be done using martingale techniques. Very clever choice of martingales. Okay, one remark: when eta goes to -infinity, Mountford, Wallerstein, and Yao have calculated the metastable exponents. They see the phase transition at this line at 2.5. They also see this crossover between strategies at the red line, because they see they just not only look at the metastable exponents, but they also take logarithmic factors into account that change here.
Sorry, Peter, and I think time is almost up.
Indeed. Indeed, I wanted to show you a bit of the martingale technique, but I have no time to do this, so I finish here. Thank you very much.
Thank you very much for this very lovely talk. I think we might have time for a very quick question. If anyone has a question, please could you unmute yourself?
Yes, I have a question. Peter, thank you very much for your talk. I was wondering if you change from this sort of Chung-Lu model to, say, a configuration model or a preferential attachment model, does the picture that you show here change completely as well, or do you see a similar picture?
So you see the preferential attachment. If you change to preferential attachment, the picture changes completely. So our proof methods work in this case, but you have different phases. You still have the same strategies, but for preferential attachment, delayed the indirect strategies are vastly more efficient. So you will have more green if you in the picture. So I mean, in the paper we also deal with the preferential attachment situation. Configuration model is not really different. I mean, it's just extremely, if you want to formulate a dynamic graph model which has the configuration model as the stationary state, it's not very natural. But everything is in principle exactly the same as here. But preferential attachment is different. So configuration model is the same. In the static case, it's actually the same. If you make it a time variable in the right way, it should also be the same. Preferential attachment is different.
Okay, so I think we have almost used the first hour. So in that case, let's thank Peter for his talk. I'll now hand over to Ganesh.
Yeah, thanks, Min. Laurent, are you able to share your slides now?
Can you hear me?
Yeah.
So let's try. Can you see the slides?
Yeah, looking good to me. Okay. Okay, good. So if you're ready, it's my pleasure to introduce our second speaker, Laurent Massoulié. Laurent is Research Director at INRIA, Head of the Microsoft Research INRIA Joint Center, and Professor at the École Polytechnique. He's received Best Paper awards at a number of conferences. He's a Fellow of the Prairie Institute and received the Grand Prix Scientifique of the Del Duca Foundation. And today he's going to tell us about tree matching and graph alignment. So I'll hand over to you, Laurent.
Thank you, Ganesh. Pleasure for me to be here. The work I'm going to present has been done jointly with my PhD student, Luca Ganassali. So to get into the topic, let me first remind you what the graph isomorphism problem is. Graph isomorphism is the following. Given two graphs, G and G prime, the question of whether there's a graph isomorphism between them is the question of whether there's a bijection F from the vertices V of the first graph to the vertices V prime of the second graph, such that the bijection carries edges to edges and non-edges to non-edges. So I've illustrated such a graph isomorphism on the picture, and it's a problem that has puzzled computer scientists for decades now. It is believed to be neither solvable in polynomial time nor to be an NP-complete problem. So it's a strange beast in the class of NP algorithmic problems. And the problem I want to consider today is a form of relaxation of this famous graph isomorphism problem, which is known as the graph alignment problem. As I mentioned, you can see it as a relaxed version of graph isomorphism. Now, given two graphs, we are no longer asking whether there exists an isomorphism between them, but we are asking whether there is a near isomorphism. That is, we are looking for a bijection, assuming again that the graphs have the same number of vertices from one set of vertices to the other, such that most of the edges or non-edges are preserved. So you can change that into an optimization problem. Formally, you may want to look for the bijection from the vertices of the left graph to the vertices of the right graph that has the least number of disagreements in terms of mapping an edge to a non-edge or vice versa. And so that's the optimization problem I'm writing here. So minimizing the number of disagreements. Seen that way, you can view that this problem is in fact a special case of something known as the quadratic assignment problem, which is to find a permutation matrix pi that maximizes the trace of the product A pi A prime pi transposed, where A and A prime are two matrices. So in our case, that would be the adjacency matrices of our two graphs. So this one is known to be a NP hard. So we are interested in solving this kind of graph alignment problem, either finding the best alignment or finding a good enough alignment of two graphs. So I'll say a word or two about applications to motivate a little bit the search for such near alignments of graphs. So I'll have several examples of applications that are really of the same kind. The first one being that of de-anonymization of social network data. So imagine you have a graph of friendship or connections among users of a social network, and you know the identities of those users. And now you have another graph of relationships of users of another online social network, say, and this time you don't know the identities of the users. If you are able to align meaningfully the two graphs of these two social networks, then you can import identities from one graph to the other and hence de-anonymize the initially anonymous data set. So there are other examples of that kind where you import information from one graph to another based on an alignment of the two graphs. One such example is when you align protein-protein interaction graphs that you may have for, say, protein interactions for two species. So you may have a complete knowledge of the function of proteins, say, for E. coli, any species that is very well studied, and so an alignment with protein-protein interaction graphs of another species may allow you to import knowledge from one species to the other. Of the same kind, if you have 3D images, say, that could be obtained through fMRI of say, a heart of a patient, and you may have processed such an image and turned it into a mesh. So you may have a mesh graph representing the surface of the heart of a patient. You may align this with the mesh of a reference heart and import annotations, information about the various parts of the heart in the reference image to the one that you are trying to make sense of. And finally, one last example that is of a slightly different kind. Consider two graphs that represent interactions between words in languages, and that could, so proximity well, connectivity of words in a language may represent the fact that they occur close by in sentences uttered in that language. So now if you manage to align the graphs representing those two languages, maybe you can have presumably not perfect, but a poor man's bilingual dictionary, allowing you to translate somehow between one language and the other. So that's what I wanted to say about motivation, and there are plenty of applications, so we can happily jump into the modeling and the analysis without worrying anymore about applications. And so we'll consider this problem in a context where we are dealing with generative models of graphs, and we'll consider what is known as correlated Erdős-Rényi graphs. So I guess there's no need to remind to you all what the Erdős-Rényi graph is on n vertices and with a parameter p for the probability of presence of an edge. So what we are going to try and do is align graphs that are correlated Erdős-Rényi graphs. And the simplest model of such correlated Erdős-Rényi graphs can be described as follows. Start off with a master graph, G naught, with n vertices and probability of there being an edge between any two vertices, P over S for two parameters, P and S. And then create a first graph G1 by downsampling edges of the master graph. So you keep existing edges with probability S, and that produces graph G1, which is Erdős-Rényi with parameters N and P, and do the same once more, so an independent round of downsampling to produce another Erdős-Rényi graph G'2 of parameters N and P as well. So you can work out the correlations between the edge indicators in these two graphs, which is what I've written down here on the slide. But you don't get to see G1 and G'2. You get to see them with the identities of the vertices erased. And so we may represent that by assuming that we have just rebaptized the vertices of G'2 applying some uniformly chosen random permutation of the integers from 1 to n, and that produces for us a graph G2 that we get to observe. So that's the generative model that we are going to consider. And so the job for us now is to recover the permutation sigma, the identity correspondences, if you like, in our two graphs G2 and G1, based on their observation. So let me tell you a little bit about prior work on the topic. There has been a number of works on exact recovery of the permutation sigma. And in a very nice paper, Kulina and Kiavash in 2016 have determined necessary and sufficient conditions for it being possible on the basis of the two graphs G1 and G2 to recover the permutation sigma. So that's the condition I'm giving here, I'm highlighting here. So this recovery is feasible if and only if the product NP, which is the average degree in both our graphs, times S, which is the correlation parameter in our joint model, is equal to log n plus something diverging to infinity. So that's the information theoretically feasible condition for our recovery of sigma. There have been a number of works addressing the question of, is there a polynomial time algorithm that allows you to recover sigma? Because in Kulina and Kiavash, the feasibility side is solved by checking a potentially super exponential number of permutations, so it's not polynomial time. So about polynomial time recovery of sigma, I'm quoting here two results. There's one by Ding et al. In 2018, which says that if average degree NP is polylogarithmic in n, and if 1 minus correlation parameter S is behaves like an inverse power of log n, then this can be done. There are a number of algorithms that have been proposed, and this is actually an active research topic. The result I was highlighting just now has been improved this month by Chung Mao and Rudolson and Tikhomirov, and they relaxed the condition of the correlation parameter to 1 minus s being less than negative power of log n rather than log n. So that's an improvement. So what we get from this first batch of prior work is that recovery of sigma is going to be feasible only if we are considering random graphs with an average degree that is at least logarithmic in n. There's no hope of being able to recover sigma otherwise. Nevertheless, we are interested in sparse graphs because these are natural models for many of the applications I've mentioned, and they call for different kinds of analysis. So we do assume in the sequel that we have random graphs of average degree order 1, but as I just said, there's no hope of recovering exactly the unknown permutation sigma, so we relax this objective, and instead we will be satisfied if we can exhibit a permutation sigma hat estimated from the observations G1, G2 that is correct on a non-vanishing fraction of the vertices. So the overlap of sigma hat with sigma that I'm defining here as the fraction of vertices I such that sigma I and sigma hat I coincide is with high probability bounded below by something that does not vanish with n. All right, so that's what we are going to try and do. And so in a nutshell, here's what I'm going to try and explain. That's the main theorem of that work. we'll see that in the sparse case, in the order 1 average degree for our graphs, so average degree will be lambda in the sequel, then at least for a range of average degrees lambda from 1 to lambda naught, for lambda naught larger than 1, there is a critical correlation parameter S star of lambda, such that for all S above this S star of lambda and less than 1, an algorithm that I'm going to explain in a minute, the neighborhood tree matching algorithm, successfully returns a permutation sigma hat that has with high probability of positive overlap. So maybe the phase diagram I'm drawing below is illustrating that in a clearer fashion. It's convenient to look at the diagram where we have, oh, sorry, I do that all the time. All right, so let me go back to the slide. So we are looking at the phase diagram where the x-axis is the average degree and the y-axis is the correlation parameter. So if our results cover the green triangle on the upper left of the diagram, and the previous results I was mentioning cover the blue area for information theoretic feasibility and the green area for polytime feasibility on the right of the diagram. And so that's what I want to tell you about, this green triangle. And near the end of the talk, I will tell you about other more recent works that have recently appeared that complement a little bit this diagram, which as it stands is not saying anything about the white area in the middle. Okay, so let's get going. I'll first tell you about tree matching weights that we will be using in our algorithm, then describe the algorithm, and try to convey the intuition of the proof by, in particular, telling you about results we can obtain for matching weights of pairs of random trees, whether correlated or independent. Okay, and feel free to ask questions as I go. I'm happy to take them at any time. Okay, so tree matching weights, they will be defined as follows. Consider two trees that are rooted. There's a distinguished vertex that is the root of the tree, and an integer d, which is going to be a depth of interest for both our trees. Then the matching weight WD of the pair of trees T prime is by definition the maximum over subtrees T second, which are subtrees of both T and T prime, of the number of leaves at depth D of that joint subtree. So I'm illustrating that on a picture with D equals 3, depth 3. And here there's highlighted in red a subtree common to the tree on the left and the tree on the right, which has 7 vertices at depth 3. So in that particular case, our matching weight would just be W3 equals 7. And one remark of interest to us concerning these matching weights, they can be computed recursively. And so if you have two trees with a number of nodes of order n, say, on both sides, then the computation time to get this matching weight is polynomial in the sizes of the two trees, measured, say, in the number of vertices. And why is that? Because to compute the matching weight between T and T prime, what you can do is consider neighbors, say I of the root of T and U of the root of T prime. Consider the, say this would be I and this would be the dangling tree from the neighbor I of the root of T, and this would be, say, dangling tree from a neighbor U of the root of T prime. So if we know the matching weights of all such dangling trees, we can sum them for every matching of the neighbors of the root on T and the neighbors of the root in T prime. And if we maximize this sum of weights of subtrees, then we get the quantity of interest. Okay, so this can be computed in polynomial time, and this is why the algorithm we are going to consider is a polynomial time algorithm. Okay, so a first attempt at defining an algorithm for matching sparse random graphs is as follows. We may say that vertices I in G1 and U in G2 should be matched if then their neighborhoods are tree-like, which is going to be the usual case in our Erdős-Renyi graphs when we are considering order 1 average degree. And more importantly, when the matching weight between the two neighborhoods rooted at the nodes I and U we consider is sufficiently large. So that's the idea we want to implement. We are going to require some finessing around this idea because it's not immune against false positives. I'm trying to illustrate that on the picture here on the slide. Imagine you have two nodes I and U in our joint graph, master graph, that are nearby. And let's say green edges are the ones in G1, red edges are the ones in G2. Then if these two nodes are close by in this joint graph, where I put the two kinds of edges, their neighborhoods would share a potentially large subtree, and so they may have a large matching weight, despite the fact that they are not a match. So to hedge against those false positives, we elaborate a little bit on the algorithm, and that's what I'm trying to describe now. So instead of just deciding to match two nodes I and U, which have a large matching weight, we are going to require that they have each of them a pair of neighbors. So say I in G1 has a neighbor J and a neighbor J prime, such that U in G2 has two neighbors, say V and V prime. Okay, so I'm circling neighborhoods of those neighbors, and we are going to require that these two trees have a large matching weight, and these two trees have a large matching weight. So we consider dangling trees from neighbors of the two nodes we're considering. And we are going to ask not just that the neighborhood and I and the neighborhood of U have a large matching weight. We are going to ask a little bit more by involving those two neighbors of the two nodes we consider. And specifically, we shall match I and U if for some depth D that is logarithmic in the number of vertices we consider, and for some threshold that is going to be set at lambda times S to the D, times some constant, then we are going to match I and U if the pairs of neighbors of both have matching weights to the depth of order log n, which is larger than this threshold tau, which is order lambda S to the D, the depth we consider. So the precise statement of the theorem we have is that if we do this, then the matches we are going to create will contain a non-vanishing fraction of correct matches and will contain a vanishing fraction of incorrect matches. And so once we have that, we are done. We can claim that we have successfully recovered the alignment, at least partially. Okay. Let's look now to see how the proof of that result can be constructed. Let's see some results about matching weights for independent random trees. This is one of the key ingredients in our argument. Consider two trees, TT prime, that are independent branching trees, Galton-Watson branching trees. And let's assume that the offspring distribution is Poisson with parameter lambda. And so one result that we do need is the following theorem, which says that for lambda larger than 1, in some range 1 to lambda naught, and for some s that is, there is some s star of lambda such that whenever s is larger than s star of lambda, then for some gamma less than lambda s, the matching weight with high probability of our two trees, TT prime, our Poisson branching trees, at depth d is negligible compared to gamma to the d. Okay, and how do we show this? Well, we show this by induction on D, and specifically we show that there is there is something like that happens. Probability that gamma to the minus D WD is larger than X is going to be less than e to the minus X minus C plus for X any non-negative real, and we show this by induction. So we show a stochastic ordering on the matching weights by induction on the depth. Okay, so how do we exploit that then? Well, we rely on the local structure of our Erdős-Rényi graphs. So it is well known that when we have a single Erdős-Rényi graph, the local structure around a vertex is close in total variation to a branching process with a Poisson offspring distribution with parameter the average degree in the Erdős-Rényi random graph. And there is a multi-type version of that result. So for instance, if we start off with our master graph and we color in, so here I guess I colored in orange the edges of graph G1 that we obtained from the first downsampling, and we color in green the edges obtained from the second downsampling to produce graph G'2 as I called it. Then the local structure of that union graph, this is what I'm calling the union graph, is again close in total variation to a multi-type branching process. And so we will have, for instance, that we have doubly colored edges which are created according to a Poisson with parameter lambda s random variable. So this is what we are going to call the intersection graph between our two graphs G1 and G'2. And we have also single colored edges. And so this is why one needs a three-type Galton-Watson branching process to reflect the local structure of this graph, of this aligned graph that we are trying to make sense of. Okay, so how do we obtain the result we want? So the first thing to note is that if we are considering a candidate match that is in fact a correct match, so we are trying to see whether we should match node U with node I in graphs G2 and G1, say, then because of this local structure result, we know that the neighborhoods of U and of I in graphs G2 and G1 contain in common the descendants in a Poisson branching process with offspring distribution that is Poisson of lambda s, that corresponds to the intersection graph, as I've called it. And so we know that because of well-known facts about Galton-Watson branching processes, the edge weight of this tree in the that is in the neighborhood of both U and I has a number of leaves at depth D that is going to be of the order of lambda S to the D. So that's something that we can obtain from this local neighborhood property, as well as the property of the branching process. So we know that if we try to match with the first attempt two nodes I and U that were correct matches with a good enough probability, we would put them in our constructed matching. And in our refined version, we would also have with a positive probability of success when we pick I and U, which are correct matches. So there is another case to consider, that is when I and U are far apart in that union graph I was depicting. Then in that case, the neighborhood of each of them in their respective graphs can be related to independent Poisson lambda Galton-Watson branching processes. And so by the result I was describing, we know that this will be negligible compared to some gamma to the D, the matching weight to depth D of these two neighborhoods, provided gamma is less than lambda S. So that's where the result on the matching weights of independent Poisson branching processes comes in. And so that is how we show that for nodes far apart, we are not going to do a blunder and match them. So there are a number of other cases that we need to consider to make sure that we don't include fake matches, or at least we include a negligible fraction of fake matches when we run our algorithms. And this is actually why we introduced the dangling tree condition for the actual version of our algorithm, where we require to include a pair IU in our matching, that they have each of them two neighbors which give rise to two matching weights that are larger than the threshold tau. And so there are a number of cases to be considered. And I guess so the picture here is supposedly exhausting the cases one needs to go through to get a proof, but the nastiest one is probably this one, I guess. So when you have node I here and node U here, and you have a pair of neighbors J prime. So here you have this J prime neighbor of I, and here V prime neighbor of U, and they do share a tree in the intersection graph in their neighborhood. So there's potential for high matching weight, and then you have another neighbor of I, J, which is here, and you may have you need to rule out the fact that there could be two large enough matching weights in the running of the algorithm. And in fact, we are led also to consider the matching weight of two correlated trees, where one has a root that is a child of the other one. So that's one of the delicate parts in the argument. And it turns out that for correlated trees where one is a subtree of the other one, as I depict here, then we get something similar to the result we have on the two independent Poisson branching processes, namely the matching weight between these two trees, one of which being correlated to the other, but a subtree of the other, increases at an exponential rate that can be made smaller than lambda s to the d. Anyhow, so let me not say much more about the proof, just a couple of illustrations. So the work is mostly theoretical, and we don't have, as of now, a very fast implementation that scales to very large graphs, but it's always good to check whether the theory is confirmed or confirms the simulations. And so that's, I guess, the purpose of the plots I want to show now. So first plot is for the case of isomorphic random graphs, that is when S is equal to 1. And so here we vary the number of vertices between, say, 20 and 150. And we run the algorithm with a little depth parameter, d equals 5. And we do see that, indeed, the matches we produce are for most of them correct matches. And as the number of vertices increases, we see that the fraction of matches we can identify increases. And here for lambda average degree of order 2.1, we get like 20%, a bit more of correct matches. And so we do see another confirmation of the theory when we look at the impact of the correlation parameter, S. Here we have graphs of size 150 nodes, average degree lambda 1.4, depth is again 5. And we see that as we increase the correlation parameter, as expected, the fraction of correct matches we find in our algorithm increases, but it's significantly larger than the fraction of fake matches, and the later going to 0 as S goes to 1 apparently, and so that's confirmation that the scheme does as expected. So that's essentially what I wanted to tell you today. I have some conclusions and also some comments on open questions and more recent results on that problem that I want to tell you about now. So I guess that's conclusion that what's nice about this graph alignment problem is that there are so many applications that you can forget about them and you can do a nice theory, being confident that it may be relevant to some applications. And there has been comparatively little work on the alignment of sparse graphs that I was describing to you today. And so in that sense, our scheme is interesting because there exists no other result about polynomial time partial alignment for sparse random graphs. So that's a nice feature of the algorithm and the results. So as I said, this is an active area. And so there have been a number of relevant results since we did that work. So I'm trying to summarize the most recent advances on the phase diagram on the slide. So I've included 3 more recent results on this diagram. So the green triangle is what I was telling you about in the presentation today. There has been work on the information theoretic feasibility of partial alignment for sparse graphs. So first work of that kind was something I did with Georgina Hall in last year. And so we showed that when the product lambda s, which can be interpreted as the average degree in the intersection graph for our model, so lambda s has an interpretation as such. So when lambda s is larger than some large enough constant c, then partial alignment is feasible in the information theoretic sense. So this has been improved last month by a very nice paper by Yihong Wu, Jiaming Su, and Sophie Yu. They showed that if lambda s is larger than 4, it is information theoretically feasible to partially align the two correlated sparse Erdős-Renyi graphs. So that's, I guess, the upper right part of this diagram with the blue area and the two boundaries, the lambda s equals 4 and the lambda s equals c curves. And quite recently, this month actually, with Luca Ganassali, my student, and my colleague Marc Lelarge, we have established that when lambda s is less than 1, then it is information theoretically infeasible to partially align the two graphs. And so that's the orange area at the bottom left of the phase diagram. So we don't really know what the boundaries between the distinct phases should look like. The one possibility is that there are 3 distinct phases. One phase where it's IT infeasible, so that would be an area that encompasses the orange area on the diagram. That there's an area where it's polynomial time feasible, and that there's an intermediate range where it's feasible from an information theoretic point of view, but there is no known polynomial time algorithm. So that would be what people tend to call the hard phase, when it's feasible but not in polynomial time. And so we don't know at this stage whether the partial graph alignment is a problem instance where those 3 phases occur, or whether we just have an impossible phase, IT impossible, and a polytime phase. And we don't know the boundary for the green area, the polytime feasible area. So this is these are all exciting open questions. Okay, and one last point is that the algorithm I've described is not so good at handling dense graphs, and as we defined it, we remove from our procedure nodes that have cycles in their local neighborhoods, which is probably a waste. And so there's also a number of open questions about improving that algorithm and fixing it so that it can handle graphs that are dense or that contain cycles. All right, and so I guess I can stop here, and thank you for your attention, and take questions if there are any.
Okay, thank you, Laurent. We have plenty of time for questions, so please put up your hand or unmute yourselves and speak. Go ahead, Shankar.
Okay, very nice talk. Just one question and one comment. So the question is, so it seems like what you're doing is you're trying to match up subtrees up to a certain radius between these two correlated graphs, and you have some optimality functional. In your case, you're dealing with the number of leaves and you're measuring these matching subtrees based on the number of leaves. But in principle, you could also do like number of leaves plus number of vertices of degree 1, or number of leaves plus number of vertices of degree 1 plus number of vertices of degree 2. And so I assume it's hard to computationally use such schemes, but do you think these can be used to improve the algorithms, forgetting about computational complexity?
So I guess we would want to have some metrics that are that deal with the fact that we expect for good matches to have a dense subtree in common, and so we would want something that is monotonic as we increase, as we add vertices or edges in the neighborhoods. it's natural to try and cook up something that would increase as you do so. So, for instance, the nodes of degree 1 may not be the right thing to include. But that being said, I would assume that you can improve this basic metric we have been using, this matching weight we have been using. So you could perhaps get a bonus when there is a high degree node in the neighborhood, so that you can match nodes with a high degree as you construct this joint subtree in the neighborhoods. You could add a bonus to that matching weight. And I guess the question, so this leads to the question, okay, you have a positive overlap with that scheme. What is the best overlap you can achieve? Okay, maybe there is something that is a function of lambda and s, that is the fraction of correct matches you can produce. I don't think the scheme we have has any chance of producing the ideal fraction of correct matches. But okay, so I guess that's another open question. Try and find a scheme which achieves the best fraction of correct matches in this problem.
Okay, thank you.
Okay, and we have a question from Ed Crane.
So, very nice talk. Thank you. Are there methods that are used in practice for this problem about which nothing has been proven, but nevertheless they work well? I'm thinking of MCMC optimization, that kind of thing.
There are a number of methods. So I think there are methods that are very domain specific. So for instance, I was talking about aligning graphs of languages. So in natural language processing, there are methods that are specific to that area. And I'm sure there are other methods in other areas, like the protein-protein graph alignment problem. I think there are methods there as well. What I know is there's a nice paper by Muriel Médard and co-workers had a nice paper on spectral methods for doing that, which so they have a number of spectral methods that seem quite reasonable. Some of them are not very expensive and can be run on sizable graphs. And we had done a bit of analysis on that. So I would say that, for instance, if you take the two adjacency matrices of your two graphs and you extract, say, the Perron-Frobenius eigenvector associated with the leading eigenvalue, and then you sort the vertices according to the magnitude of the entry in the Perron-Frobenius eigenvector, that gives you a cheap, reasonably cheap way of aligning the graphs. It's not going to work well in the sparse regimes that I was describing, but if you have a lot of structure, this could be a good subroutine. You may improve it by combining it with other things.
Okay, thank you.
You're welcome.
Thanks. I had a question. So your original graph may itself have lots of automorphisms, and you can only match up to automorphism. Is much known about how these change with the parameters?
The number of automorphisms of a graph?
Mm-hmm.
So I think for a single graph, there is a paper by Luchak, which I've printed and I've read most of it. And I think it gives a sharp asymptotics on the number of isomorphisms of graphs. So, but essentially, okay, so the small connected components give rise to lots of automorphisms. So you can, do any permutation on the isolated vertices and isolated edges. So typically your graphs have those order n small subtrees as connected components. And for these, that creates a corresponding number of automorphisms. And then you have the giant component for which I think there is no automorphism except the identity. I'm not 100% sure about this last point, but I think this is in the paper of Luchak.
Okay, thanks. Thank you. Okay, any more questions? If not, let's thank Laurent for a very interesting talk. Okay, and we'll start in 5 minutes with the last talk. So welcome back, everyone. It's my pleasure to introduce our last speaker today, who is Shankar Bhamidi. Shankar is professor in the Department of Statistics and Operations Research at the University of North Carolina and a fellow of the IMS. And today he'll tell us about long-range dependence and evolving networks.
Okay, again, many thanks for the invitation. It's also maybe good that this talk is being recorded, because then all of you are spared from any of the really poor jokes that I usually start talks with. Sort of coincidentally, this talk is related to the two really nice talks that just came before. And so there are two themes to this talk. So the first one vaguely related to anomaly detection and change point. So the story behind this sort of theme is, imagine you have a big social network that has a lot of influence on the world. Let's make up a fake name, like Fitter or something. And let's say there's some big event happens. For example, a famous, highly influential person, for whatever reason, has been removed from the system. And if the dynamics, so these are dynamic networks. I'm mainly interested in networks that are changing over time. Suppose the system was evolving according to some stationary process up to this big change, and then it changes the behavior, it changes how it's behaving or how individuals in the system are behaving. Can you detect based on just slices of information? You don't actually know what happened. Can you detect a change happening just from the network information itself? And the second question is quite related to the Professor Massoulié's very nice talk just now. And so the goal of this second theme is, again, suppose you have an evolving network starting from some initial seed. And so, for example, because we're in COVID times, you could think of infection starting on some sort of fixed network or a network itself growing over time. And so suppose you start from an initial seed vertex, and at some large point in time, let's say where the network is, I don't know, 1 million vertices, you just observe the network structure without any sort of time information. Okay, so you just observe one slice of the network, you know who's infected, and you potentially know the connections between these people, but you don't know how the infection itself sort of progressed through the population. Then, or let me change it in terms of just the last talk. Suppose you have two networks, for example, protein-protein interaction networks, one for humans, one for E. coli. Suppose they start from the same base graph, so to speak, but at some point in time, they diverge in their evolution. So up to a stage, they're identical, a seed graph. And then after this time, they start diverging and they evolve in their own independent fashion. Now, the basic question you could ask related to the last talk is, suppose you're given protein-protein interaction networks for humans, protein-protein interaction networks for E. coli. Can you sort of match these up in some fashion? So this network alignment. And perhaps unlike the last talk, the question that maybe I'm interested in is, suppose you actually have an evolving sequence. So you don't have these networks on some fixed size of size n, on which the edges are somehow correlated, but they start from the same seed graph and then eventually sort of branch off. Can you use, is there this long-range dependence, potential long-range dependence in the evolution? can that be used to somehow align things? So I won't go to the alignment problem itself, but more sort of, can you detect the initial seed? So potentially, if you can detect an initial seed, then you can use this maybe in a recursive fashion to align the two networks. And sort of, this is the only main message. And after this, you can sort of zone out. So there are powerful tools from probability, something called continuous time branching processes, which seem to provide key insight into such questions in the for temporal networks. And this notion of long-range dependence, so the effect of the initial seed, this is a recurring theme that seems to keep showing up in many such questions. And it has, so in the two stories that I'm going to tell you, it has a dual purpose. So it makes problems like change point detection hard. And many of the things that people say in statistics have been using, like classical change point detection methods, they don't quite transfer to the network setting. But on the flip side, if there is a lot of dependence of the initial seed, it could allow, if there's a lot of long-range dependence, it could allow the detection of the initial seed quite easily. So these are the main messages, two sides of the same coin. Okay, so the plan for the talk, I'm going to start with change point detection for networks, just because it's easier, it's much easier to see this long-range dependence. So I'll tell you a little bit about the motivation. I'll try to tell you about non-parametric change point detection and more refined. So non-parametric meaning when you don't know the exact probabilistic model underlying the dynamics of the network. And then I'll tell you more refined results if you can assume something called linear preferential attachment. And the second part is the seed detection. This is a largely joint work with Sain Banerjee. And here I'm going to tell you things like vertex score functionals, notions of persistence and robustness, and something called centroid centrality that allows one to sort of match up, not match up, but detect the initial seed. And then I will end the talk with something that is, we were highly influenced by the work of the first speaker, Professor Mörters and his collaborator, Dietrich, where in, I think, 2011, they had a, now in hindsight, a very influential paper about persistence of hubs in networks. And so sort of more local degree-based measures. So much of this talk has, precise statements and so on. Fortunately for, I think, everyone concerned, I'm just going to skim through it. So each slide, I'll just try to tell you the main, what this slide is talking about without spending too much time on the exact statements. Okay, so let's get started. So the first area is this change point detection. This is a fundamental area in statistics and applied probability. If you haven't seen this before, sort of the maybe the base case is the following. So suppose you have a sequence of real valued random variables, xn, x1, x2 up to xn. And suppose there's a fixed gamma in the interval 0 to 1, and you have two CDFs f and g. And all you know about the sequence is the following. Up to time n gamma, these xm's are IID with distribution f. And for time greater than n gamma, so from time n gamma all the way to n, these xm's are IID with this new distribution g. And non-parametric change point means, suppose the only information you know is that f and g are different. So there is a change in the system. And as a small remark, in the world of change point, this is already a huge assumption. So there's a one step before this where one would like to test the hypothesis that there was actually a change point. But let's just assume that you know there's a change point. Then the main question is, can you estimate gamma just using your sequence? And can you, for us as mathematicians, our main goal would be, if someone has come up with an estimator, can we understand things like consistency and distributional properties of said estimator? So sort of one of the fundamental results in this area, which goes back all the way to 1988, by a work of Karlstein. So what he did was he said, okay, for each candidate time t, you can look at the empirical distribution of the observations up to time t. You can look at the empirical distributions after time t, so from time nt plus 1 all the way to n. you can look at the distance between these two empirical measures, and your favorite notion of distance, Kolmogorov-Smirnov, Wasserstein distance, whatever you want, as long as they're able to differentiate things. And you need to multiply by a factor so as to get rid of what happens at the beginning and what happens at the end. You want things to sort of stabilize. And then he showed once you do this, if you look at sort of the maximum of this sort of function, this is a random function defined on the interval 0 to 1. If you look at the maximum of this, that's an estimator, and it's a consistent estimator. And following this, there's been a lot of much more precise work in this sort of area. Okay, let's switch now to network change point. And so there's a reasonable amount of work in the applied literature in the slightly different area of trying to understand in a fixed network interesting anomalous regions, so anomalous subset detection. There's been an enormous amount of work in the area of community detection. So our main math motivation here is slightly different from, say, community detection. So here we have an evolving network model. So you have a network starting at some time point, 1, and then it keeps changing in some fashion. And suppose the original network was formulated, so people made this network model for some particular purpose. For example, they were thinking about a network model that could explain heavy tail degree phenomenon. Now, suppose this network uses one set of parameters in its evolution up to time n gamma. So these parameters don't change up to time n gamma. And another set after time n gamma. So from time n gamma to n, it uses another set of parameters. So there's a change in the evolution of the system at time n gamma. So the two main questions we're interested in is, can we understand the effect of this change point on structural properties of the network? Can we understand change point detection? And the second question is, can we actually formulate change point detection estimators? How do classical methods sort of carry over? So these are our main math motivations. So the main model of networks we're going to use throughout the talk is this so-called preferential attachment class of models. And so it's, although at the end of the talk, I'll tell you about non-tree versions. It's easiest for the talk to just think about a sequence of networks which are always trees. So, so here you start with some fixed function, f0. I'm putting f0 because this is the initial parameter. Some function f0, which is used to measure if you have a vertex of, let's say, degree. So it's 0 because I'm going to rephrase things in terms of out degree. But broadly think of this function f0 as saying if a person has a degree 1 in the network, f0 of 1 says how attractive this person appears for a new person to try to connect to them. So you have this fixed function f0. And so what we're going to do is we're going to grow a sequence of random trees, tau n, where you start with a root attached to a single vertex. And at each stage, a new vertex arrives and connects to a pre-existing vertex randomly with probability proportional to this function of the current out degree of that vertex. Okay, and then the out degrees get updated, the attractiveness of different vertices get updated, and this process continues. So for example, you have this new vertex 3 that enters the system. In principle, I should have put f0 of 1. The root has f0 1 as its attractiveness because it has 1 out degree. Again, ignore out degrees, etc. This is just for mathematical trying to be overly precise. So f0 of 1 for the root, f0 of 0 for this vertex 2, and this vertex 3 uses these weights to figure out who to connect to. So let's say it connects to the root. Then each of these vertices now have their corresponding attractivenesses. So the root has f02, vertex 3 has f00, vertex 2 also has f00, their attractivenesses, and vertex 4 comes and decides to connect to vertex 3. And then now all the attractivenesses get updated, and the system proceeds in this fashion. So sort of one of the most famous class of such models is the so-called affine preferential attachment, which has been there in our probability community all the way since the work of Yule in the 1920s. So here broadly, the attractiveness of a function, attractiveness of the degree of a vertex of degree k is basically the degree plus a parameter. Okay, so you have this vertex. In this case, at this stage, these vertices, so vertex 3 has degree 1, essentially, or out degree 0. So 0 plus 1 plus alpha, etc. And the process evolves in this fashion. So this one was came to sort of the, let's say, came back in popularity in the 90s when people started, late 90s, so 1999, and then early 2000s when people really started looking at real world networks, seeing that maybe some of these didn't have the characteristics that one was looking at for the currently proposed network models at that stage. And we're trying to come up with simple rules that could give you things like heavy tail degree distribution. So in particular, for this, in the general case, for general attractiveness functions, F0, if you make some assumptions on this function F0, which I'm going to skim over, but bottom line, someone comes to you with this attractiveness function F0, if you can form an associated function, this rho hat lambda, which is this infinite series, for each fixed lambda, you have an infinite series with this lambda term appearing here. Again, none of the details important. So someone comes to you with this function F0, you form this function rho hat lambda, it could become infinity at some stage, but hopefully under good conditions, it's finite for over some stretch of lambda, and it takes a value above 1 at some point. You try to solve the equation rho hat lambda equals 1. You try to solve this sort of equation. And if you can do this, then all the way going back to the 1980s and 90s, work of Jagers and Nerman, and then later Aldous, Ballantot, and Arrudas, etc. Their work, what it says is for these preferential attachment type models, you can, the degree distribution, if you look at the number of vertices of degree k, then the degree distribution converges to a limit constant pk, which looks like this, okay, expressed in terms of the attractiveness function and this constant lambda star. So a lot of precise results are known for these sorts of models, and in particular, it excited network scientists because it showed that if you chose, for example, this linear preferential attachment, so probability proportional degree plus alpha, then the limiting degree distribution of your network had a heavy tailed degree exponent. So scale like alpha plus 3. Okay, and it also, the much more deeper results were known. I should have put Mori proved that if you look at the maximal degrees, then these scale like this n to the 1 plus alpha or 2 plus alpha. Okay, and so the main preferential attachment change point model is, so my plan is, it's my time 11:18. I'll spend about 12 more minutes on this and then switch over to the seed problem. Okay, so the change point model is now you have two functions, F0 and F1. The system uses this function F0 up to time n gamma and uses this different function F1 from time n gamma to n. Okay, and let's say you don't know anything about F0 and F1, modulo, of course, technical assumptions. Can you estimate things like this gamma? So, and I keep talking about long range dependence. So what you'll see is the effect of the initial, however small in this version of the model, however small gamma is, even if gamma is like 0.000000001, because we're scaling things by n, essentially F0, the initial function, determines much of the properties of the network. So one could think of a version which we're vaguely calling the Big Bang model, where something happens way back in time. So at time n to the power gamma, so from time 1 to n to the power gamma, where again gamma is a parameter between 0 to 1, vertices use this function F0. And then at time n to the gamma, so for example, at time square root n, all the way up to n, our vertices, the vertices that come after this, use this different function F1. So way back in time, something happens, and after this, the system mostly uses F1. And okay, so the main math questions of interest is how does this change the structural properties of the network? For example, people formulated these models for having heavy tail degree distribution. how under change point, what happens to the system, what happens to things like maximal degrees, and are there settings where there is no change in the, although there's a change in F0 and F1, there is no change in the actual degree distribution itself. So you can't even observe the change point. And the final question is, can you estimate the change point? Let's say if you see the slices of all the slices of the network, can you estimate this change point, even though you have no information about F0, F1, and of course, gamma? So these are the sort of math questions of interest. I'm going to, so just for you to, if this general F0 and F1 seem a little abstract, in your mind, you can fix the specific case where vertices perform preferential attachment with degree plus alpha, so linear preferential attachment up to time n gamma, and then use a different parameter beta from time n gamma to n. Okay, and so to maybe give you intuition, I need a sort of 3 ingredients. And so the first ingredient, so again, remember someone has come to you with potentially two functions, F0 and F1. For the time being, let's just say you have one function F. So the first ingredient to tell you the main results is a sort of associated point process. So to generate the point process, essentially what we're going to do is we're going to generate a bunch of exponential random variables, E0 having rate F0, E1 having rate F1, and so on. And we're going to view these as the inter-arrival times of this point process. Apologies, I know it keeps skimming here. So E0, so the first point shows up after time E0, the next time shows up after time E1, and so on. And there's a slight variant of this where, let's say you erase E0, E1, and E2 and E3, and you start just with the first point showing up at E4, the second point showing up at E5, and so on. So these two sort of are one point process and a slight variant. The second is a continuous time branching process. So I'm sure there are many experts actually in the audience who know this. And if you haven't seen this before, I will give you pictures in a little bit. But a continuous time branching process, given a particular point process like chi f. So going back here, suppose you have this sort of point process, then a continuous time branching process using this as its driving parameter is the following. So you think that you have a so if you're familiar with discrete time branching processes, continuous time branching processes are essentially the same, but now you also keep track of when people gave birth to their children. So you start with a vertex, it gives birth to its first child at this time, second child at this time, and so on. And each of the individuals that are born have their own independent copy of the same point process, and they give birth to vertices in a statistically identical manner. So that's basically what a continuous time branching process is. So given a point process, you can define such a branching process. And given a continuous time branching process, you can measure various things about it. So you can measure, for example, at any time t, you can measure the number of individuals in the system by time t. You can measure the expected number of individuals by time t. You can measure the number of individuals who have k children exactly by time t. I should have said expected number of individuals with k children. And there was this variant where we started with, so you could start with the root having a slightly different offspring distribution. So this variant of the point process, and then everyone else behaves as they usually do. Okay, so there are various functionals you can measure about this branching process. Okay, and so the mental picture to have is a continuous time branching process means you have a root which gives birth at various times, and then each of these individuals, so at a continuum of times, and each of these individuals then give birth to their own children, again at random times, and the point process, for example, of this has the same statistical properties, so is independent but has the same distribution as what happens to the root. And if you fix any time, so for example, in a computer, for example, let's say I ran an algorithm to generate a continuous time branching process, I can stop it when it has some fixed number of vertices. So here I stopped it when it has 15. So tau 15 represents the stopping time when the size of the population is of size 15. And what I could do is I could just keep track of the genealogy of the corresponding tree. So this is a root. It had children 2, 3, 5, whatever this vertex was, and this vertex. So these are the corresponding vertices over here, and so on. So I could either keep track of the entire information about the tree, or I could just keep track of the genealogical information. Okay, so about 8 more minutes before I need to switch. But okay, so what I'm trying to do is I'm trying to build up to for change point detection or change point models, what can you say about asymptotic properties of the trees? So the final thing I will need to tell you is once you have all these branching processes, etc., you need this operator. This operator, what it does is it has 2 inputs. It has a number A, which is positive, and you have to plug in probability mass function P. And what it does is it uses these expectations related to the branching processes to this branching process to give you, it outputs another probability measure, probability mass function. So input is a probability mass function, output is another probability mass function. And what is this A? So this choice of A is I can choose whatever A I want. And so basically what I'm interested in is I'm interested in this change point detection. So going back to the actual model over here. So what I'm interested in is, I hope that between time 1 to n gamma, using previous known results, Jager's, Nerman, etc., I know properties about the degree distribution. But at time n gamma, there is a change in the system. And so at any time nt between n gamma to n, so a t between gamma to 1, I would like to understand the degree distribution of the network. And so this is what I'm trying to build up to. So given any such time t, what I first do is I solve this sort of weird looking equation. So I find this number AT, which solves this equation. So as an input, it uses the probability, the limiting degree distribution before change point. It uses stuff about what happens after change point, so the function after change point. It uses things related to the branching processes. None of these are important, but bottom line, it plugs all of these in, and for any time t, it tries to find an AT that solves this equation here. Okay, and so now I can tell you what the first main result is. So if you look at, so remember you have a change point at time n gamma where the system changes its evolution from F0 to F1. So write this NNKNT for the number of vertices with, again, forget about out degree, but let's say you're interested in the degree distribution. This should be NN, not DN, apologies. So write NNKT for the number of vertices with degree K in this tree after change point, NT units after change point. Then using everything on the previous slide, you can sort of keep track, not just at a fixed time, but in a supremum sense, you can keep track of the degree distribution, the evolving degree distribution of these networks for any fixed time in the interval gamma to 1. Okay, and these sorts of results are important because you need a strong control on the evolution of things like the degrees to propose change point detection algorithms. I should mention, I should have started at the beginning, this entire area is completely open. So one of the reasons I like to give this talk is, especially for, say, junior researchers, I'll be telling you about various results, and I'll show you how these results do in practice, namely on simulations. And you'll see the math results is a huge gap between saying something goes to 0 as n goes to infinity and actually coming up with something that might be even remotely useful in practice. But so what do the math results tell you? So the first thing they tell you is, irrespective of how small this gamma is, the initializer function f0 always wins in the following sense. If the degree distribution for the model with no change point, so you're just using this attachment function f0 forever, there's no change. Suppose this model had exponential tails, then so does the model with change point. So even if you switch from, let's say f0 is equal to 1 for a long period or for some time, n gamma, and after n gamma, you start doing preferential attachment type dynamics. So degree attachment with probability proportional to degree plus alpha. Then it doesn't, irrespective of what gamma is, however small, your system will still have exponential tails. It won't have heavy tail degree distribution. If the degree distribution had, with function f0, had some sort of power law tail, then the same exponent, you have the same exponent even for the model after change point. And you have similar implications for maximal degree behavior as well. So the reason why this might be important in, say, areas like heavy-tailed, like people interested in heavy tails, is what this means is just trying to estimate the exponent of the network and trying to see when the degree exponent changes. These methods don't really work in practice for such models. Okay, and so now we know in terms of structural properties, irrespective of how small gamma is, in no way does it change the degree exponent or structural properties of the degree distribution. So, but what we can prove is if the models started just with f0, if you have that network model, if it had 1 degree distribution, and if you started another model with just f1, again, no change point, if both of these have different degree distributions, then doing a change point at some point gamma, the resulting degree distribution itself that you get is different from the one without change point. So there is a difference in, like, maybe not degree exponents or exponential tails, etc., but the degree distribution itself changes if there is a change point. So using this math result, what you can do is the following. So this there are lots of notations here, but let me just try to give you the basic idea. So you can observe, so fix a sequence hn going to infinity, but slower on the logarithmic scale compared to n. And what you do is you look at your tree or your network at time n over hn. So because n over hn is still going to infinity, the hope is if you look at the degree distribution at this time of the tree, so way back in time, but still the degree distribution at this time, you have a good idea about what the degree distribution should be without change point. So look at the degree distribution of the tree at this time, and for any candidate time, so suppose someone comes and tells you, I think a change point happened at time n times 0.5, you can look at the network at that time and compute the degree distribution at that time. And you can sort of measure the distance between the degree distribution at this time nt from this time n over hn, where hopefully things have stabilized. So this is just a sort of distance between these two degree distributions. You can see when this distance starts becoming big. So hopefully for a long period before the change point, it's close to 0. But then after the change point, slowly this distance starts increasing because there is a change, or there is a change in the degree distribution after change point. So you can try to signal to, if someone is interested in change point, you can try to signal. You try to find the first t where this distance starts increasing. Okay, and your estimator for change point is this sort of, so this is your estimator for change point. When does the distance start actually becoming significantly different on the 1 over hn scale from, the 1 over bn scale from 0? And so the math result says that this gives you a consistent estimator. But if you actually try to do this on simulations, using made up things like log n, et cetera, so the blue bar over here is what the change point detection estimator that we proposed. So here the system is moving from linear preferential attachment to sublinear preferential attachment. So this blue curve or this blue block is what our change point detection estimator is sort of trying to capture over many simulations. And this is the true change point. So the change point happened at time 0.5. This is the true change point. So as you can see, although we can say that, as n becomes large, we get consistent estimators, in practice, this doesn't really do a good job. So one open problem is, so we've established various math results. Can you improve these math results to actually get something useful? In the maybe 5 minutes before I switch to the next topic, maybe let me just say a little bit about the quick Big Bang. And until about 2 weeks ago, I didn't realize that people in the anomaly detection community are actually very interested in these sorts of models. So their idea is, so change point detection tells you one sort of probability model where you have something happening up to some time gamma, and then something else happening after time gamma. But there's something called event detection, where you have a system maybe evolving according to some fashion. There's a small event, a small window where something changes, affects the network. And then after this threshold, this small time window, again, the network switches back to its old way of behaving. And so the question that people in, say, computer science are interested in is, based on these network slices, can you detect an event? So a baby version of this is a so-called quick Big Bang model. So here the change point is at time n to the gamma. So for example, at time square root n. Okay, and so up to time square root n, let's say, the network uses some function f0. From time square root n all the way to n, the network uses this function f1. So the first result, what this says is, if you look at the degree distribution of the network, the degree distribution doesn't feel the effect of the initializer, the function f0, because this time square root n is just not enough. And the limiting degree distribution is the same as the model with just run using function f1. So the degree distribution doesn't feel the effect of this change. But for specific examples, so for example, suppose you move from a uniform attachment model to a preferential attachment model. So initially, the network evolves using function f0 up to, let's say, time square root n. F0 is equal to 1. And after time square root n, you switch to a different linear preferential attachment. Then what this says is the things like the maximal degree do feel the effect of this change point. This change point gamma, although really small in terms of the scale in which you're observing these evolutions, it does have a big effect on the scaling of the maximal degree. And similarly, if you switch from linear preferential attachment to the uniform attachment, etc. So macroscopic functionals like maximal degrees potentially do feel the effect in the quick Big Bang, but more sort of law of average type things like degrees, these do not feel the effect. Okay, so I'm going to skip over all this and just try to give you some intuition in 2 minutes and then switch to the next topic as to why, in many of these cases, the initial part of the network has such a big effect. So this goes back all the way to the work of Carlin and Atreya. So remember, so let's just focus on linear preferential attachment, where at each stage a new vertex comes in, and you attach to an existing vertex v with probability proportional to essentially the degree of the vertex plus some alpha. So bottom line, you have a system, and each vertex in the system has some weights, and you want to choose these vertices with probability proportional to these weights. So Carlin and Atreya, and for those of you who've seen continuous time Markov chains, this is a very standard concept. If you have a bunch of vertices, 1, 2, and m, with associated weights w1, w2 up to wm, suppose you want to select vertex I with probability proportional to wi. So what is an easy algorithm to do this? Well, first generate a bunch of independent rate wi exponential random variables. So each vertex I has its own exponential random variable, but with rate depending upon these wi's. Look at the index which is the smallest, so at which the minimum happens. And if you look at that index, j, probability j is equal to I is equal to wi. Okay, so you have these you can pick weights, pick vertices with probability proportional to weights using independent exponential random variables. And so just a simple generalization of this is the following. So if you look at this continuous time branching process, so someone comes to you with and tells you, please construct for me a preferential attachment model with where vertices connect to previously existing vertices is probably proportional to the degree plus alpha. So, so what you do is you say, you have come to me with a discrete model, so a model where vertices are coming in one at a time. First, what I'm going to do is I'm going to construct this continuous time branching process where I use what you told me to construct this point process. Now every vertex has, I have a continuous time branching process where every vertex has offspring distribution given by this continuous time branching process, by this offspring point process, where I construct this point process using what you told me. And each node then behaves in its own fashion. Then, because of the simple properties of exponential random variables, what you can show is, if you look at the genealogical tree, so someone tells you, construct for me the network with 15 vertices. What you can do is, in a computer, you can run this continuous time algorithm, wait until it grows to size 15, let's say, n is equal to 15, and just look at the genealogy of the tree that you get at this time. And if you look at that corresponding tree, that has the same distribution as this discrete time tree that someone asked you to construct. So going back to this picture here, so you run your continuous time algorithm in the computer, wait until it grows to size 15. That's what someone wants you to construct. Look at the genealogy of the corresponding tree. This genealogy, this tree over here, this tree has the same distribution as a preferential attachment network. Okay, so this is the connection between preferential attachment networks and continuous time branching processes, and you can easily modify this to come up with corresponding versions for change point algorithms. And so, at this stage, I haven't done anything. I've changed a discrete time problem to something that happens in continuous time that maybe probabilists are more familiar with. So the question is, so what? And now let me tell you why why you see what you see in change point. So for models without change point, so for this original continuous time branching processes, there's an enormous amount of work about asymptotics. In fact, it was conjectured all the way back to Euler. He sort of said, intuitively what the population distribution should look like. And this was sort of proved by Jaggers and Nerman in the 80s. And essentially what they showed is that these branching processes, similar to discrete time, they grow at an exponential scale. This exponential scale lambda, this depends on your model. And okay, so there's a precise result here, but the punchline for us is if you use your computer to construct these continuous time versions first, and then look at the genealogy, then the amount of time for you to construct a network of size gamma n grows logarithmically in the size of the network. So some constant, this depends on your Malthusian rate of growth of your model, times log of the system size, plus something which is of order 1. So you have to essentially wait for logarithmic time in your computer for you to generate such a network. But now, so after time gamma n, let's say your network now changes and uses a different set of parameters. For the specific case of preferential attachment, like linear preferential attachment, no general functions f0, f1, but just you're doing preferential attachment with a new parameter, degree plus beta, after time gamma n, you can actually track down, you can construct precise functionals, like this process M1U, which turns out to be a martingale. And using properties of martingales, you can sort of understand what is the size of your process after change point. So the evolution of the system size after change point. But if all of this seemed a bit hazy, let me just come to the main punchline here. So because things continue to grow exponentially after time n gamma as well, what all of these probability statements, what they imply is the following. So remember, at time gamma n, so in continuous time, this tau gamma n, your system changes to something else. Now you could ask, how long does your system need in this continuous time story to go from size gamma n to size n? And what all of these probability statements tell you is it takes you only an order 1. So this time a is this constant. It takes you this time a, like 2 units of time, to go from time gamma n to time n. And so this is why in the continuous time analog, it shows you why the initializer always wins. Because this is the initializer has a long period to sort of stabilize the system. And then even though you have change point from gamma n to n, in the exponential scale, this is only order 1. So it can't really change properties of the system. Okay, so this was related to change point detection. I'm going to skip over all this and sort of just switch over to detection of the initial seed. And so the main goal here is, so unlike the previous story where I'm assuming I have observations of the entire, all the time slices, and I'm trying to do something using all these time slices, here the goal is the following. You only have observation of your network at a single large time n, and you only have topological information, so who is connected to whom, and no time labels like who's vertex 1, who's vertex 2, and so on. And so the basic question is, can we recover the initial seed? Okay, and the network model again is the same as before. You have this now no change point. You just have this function f0, which controls the dynamics of how your tree is growing. I'm going to skip this here. So the two pictures maybe to keep in mind is the following. So suppose your function f is equal to k, so the so-called preferential attachment. And so at a large period in time, you observe your network. Now here, although this might not be visible, I colored the initial vertex. So this started at vertex 1. I colored it red, which is right in the center of this graph. So when f of k is equal to k, in principle, maybe things like degrees. So you look at the vertices with large degrees, and maybe that will help you narrow down where this red vertex actually is, namely the seed of the seed of your network. Now, suppose you have a function. Sorry. Suppose your function f is equal to 1. So what this means again. So what this means is at each stage, a new vertex comes in and connects to a uniformly chosen vertex in your currently existing tree. Okay, so everyone has the same attractiveness function at every stage. So in this case, using things like the maximal degree does not work. And again, maybe this is not too easy to see, but the seed vertices, so I colored 1, 2, and 3, the three vertices that came at times 1, 2, and 3. So they're again somewhere over here. And as you can see, using things like the maximal degree, for example, it's not going to be possible to say that these are the original the people that came first in the network. And the amazing thing established by Bobek, Devroy, and Lugosi, what they showed is even in things like this, where it seems like there might be no hope in finding the initial seed, one can in fact find these initial seed vertices with using a fixed number. So basically, there is an algorithm which says, I'm going to output 10 vertices in the graph, and with reasonably high probability, one of those 10 vertices will be the original seed. So that is sort of the amazing thing that they showed, and this is what these are the sorts of problems that I've been thinking about. So let me just try to formally set up the problem. So suppose G is the space of equivalence classes up to isomorphisms of finite unlabeled graphs. So if you have two graphs with the same topology, then you sort of glue them together, not glue them together, but you think of them as in the same equivalence class. Now, if you have a finite label graph, like a graph labeled vertex, this is vertex 1, this is vertex 2, etc., then G with this circle is the isomorphism class of G. So what this is saying is, suppose you forget about the labels, then now you have an unlabeled graph. Look at the isomorphism class of G over here. So someone has deleted all the labels and just given you the topological information. Now, what a root finding algorithm is the following. So for a root finding algorithm, you need to provide a budget K. Then what it does is, so a root finding algorithm of budget K is the following. So it's a mapping HK. What does this mapping do? As an input, it takes a finite unlabeled graph G. Okay, you plug in a graph with just topological information, and the output is a subset of vertices from that graph G. So subset of vertices from that graph G. And the number of vertices that you output is k. So that's called the budget of this root finding algorithm. Now, what is our main goal? So this was sort of formalized by a whole bunch of people over here. So our main goal is the following. So suppose you have a probabilistically evolving sequence of networks started from some seed vertex, and you have an error tolerance, epsilon. Okay, and what our goal is we would like to come up with an algorithm and a budget k. So an algorithm, so I should start with a k and a corresponding mapping hk. And what this does is it takes your graph at time gn and outputs a set of vertices, k vertices from the graph gn. And what we would like is this k should be fixed, for example, 10. I mean, it will depend on epsilon, obviously, your error tolerance, but it's fixed, doesn't depend on the size of your network. And what you would want is, however large your network is, you only need, let's say, 10 vertices, so that with high enough probability, so probability 1 minus epsilon, you are able to detect the initial vertex, vertex 1. So punchline, can we choose this k, this budget, which is independent of n, and of course it will depend on epsilon, your error tolerance. What is the dependence of this error tolerance upon the actual probabilistic model of your network? So if you have, so do you need a smaller epsilon or a larger epsilon for, sorry. So for a fixed epsilon, will your budget k be smaller or larger, for example, for preferential attachment versus, let's say, uniform attachment? So the dependence on the budget based on the actual probabilistic model. So these are the main questions that we're interested in. And a sort of slightly dual question to this. So before going to the dual question, sort of the most natural mechanism for root finding algorithms is via so-called centrality measures. So what this means is you can fix your favorite measure, which takes a graph and tries to tell you how central a vertex is in that graph. So for example, you could say vertices with high degree, I think they're central in the graph. Then this would correspond to something called hub centrality. You could say, I think a vertex is central in the graph if lots of shortest paths have to pass between it. Then this is called betweenness centrality. And I'm going to come to something called centroid centrality in a little bit. But you can fix a centrality measure. These measures have to be dependent only on the topology of the network. We don't have access to things like time information. Now, given a centrality measure psi, you can, for any fixed graph G, you can compute the centrality measure of that vertex phi. And your root finding algorithm could be the following. For a fixed k, your root finding algorithm hk, using that centrality measure C, applied to a graph G, is it outputs the top. So for example, the k maximal degree vertices, etc. So this could be largest or smallest, depending upon how your centrality measure behaves. But you output the top central vertices in your graph. And then the hope is maybe this might give you a good idea about the original seed or the original vertex that started the entire network process. Sort of a related notion called robustness. So this goes back, or more precisely, persistence. This goes robustness of your algorithms, but it goes under the name of persistence. So this goes back to the work of actually the first speaker, Professor Mörters here, and Jog and Low. So you say for centrality measures C and a sequence of network models Gn, you say that, and a K, I'm sorry, and a K, you say that this sequence of networks is psi comma K persistent if the following thing happens. So if you keep trying to find central vertices, the K central vertices using the centrality measure C on your sequence of graphs Gn, then eventually within finite time, they don't change. Their identity doesn't change. So the optimal K vertices, V1 at time n applied to graph Gn, V2 applied to graph Gn, the Kth central vertex of at time Gn, this remains the same after a point. So for example, if you were doing degree centrality, what this means is the after some finite time, random, so for example, after time 25, the largest degree vertex, the second largest degree vertex, etc., their identity doesn't change. So nobody can beat them. No one can overtake the maximal degree vertex after time 15. The maximal degree vertex is fixated and remains the same forever. After time, after this random time, after this random time 15. So this is this notion of persistence. Okay, so let's go back to this example. So I have at most 5 more minutes. So let me tell you what is maybe the main measure in the community that people have been able to show does a good job. So we want to measure C, that measures centrality of the network. And things like uniform attachment, degrees don't do a good job. So we want to measure C that tells you, but still is able to tell you that, for example, these red vertices here are central compared to, let's say, more higher degree vertices. So for trees, there's something called the Jordan centrality. And so this slide has the precise statement. And in the next slide, I have a picture of this. So the centrality measure is the following. So suppose you're given a tree T. Again, you have only topological information. You measure the centrality of this of a vertex in that tree by doing the following. So you look at all children of that vertex T, of that vertex V in T. And you look at the subtrees. So maybe let me just go here. So suppose someone tells you, I think V is the root of your tree. Then what you do is the following. So you say, okay, you're telling me V is the root. What I'm going to do is I'm going to look at the three, in this case, 3 subtrees of this vertex V. I have a green subtree here, I have a purple subtree here, and I have a yellow subtree here. I'm going to look at the sizes of each of these individual trees. So this one has size 3. This big one over here has size 9, and this one has size 1. And so my centrality measure is equal to the maximum of these subtree sizes. So in this case, the centrality measure V is equal to 9. So just as an example, suppose someone says, I think this vertex, so a leaf, is the root. So if you computed the same quantity for a leaf, then the corresponding size would be n-1, because all the other vertices would be in that corresponding subtree. There's only one subtree of size equal to the size of the network minus 1. So that would have a large centrality measure, much larger than 9. Okay, so in this case, for this centrality measure, bigger is worse. Okay, so I have 2 minutes. So let me just tell you what are the main some themes. So the main results that we were able to show with Sayan Banerjee, who's a faculty here at UNC, one of my colleagues. So we were able to show that under general assumptions on your attachment function F, you can come up with sufficiency bounds. So this says that for any fixed epsilon, you need at least 1 over epsilon to this power. So this power depends on the properties of your attachment function. But if you have at least this much budget, then with probability at least 1 minus epsilon, you are able to find the root by outputting the maximal size centrality vertices, actually minimal size centrality vertices. And we also found sort of necessary bounds that any root finding algorithm, if you're using a root finding algorithm using these sort of centrality measures, you need at least so much budget to sort of find the corresponding root. And so what's the bottom line? So what this says in 1 minute. So if you have uniform attachment, f of k is equal to 1. So everyone has equal popularity at every time. You need order 1 over epsilon budget to be able to recover the root. So you don't need, however large your network is, it could be 1 million, trillion, quadrillion, etc. If you have a budget of size 1 over epsilon and you do this Jordan centrality and output the largest centrality vertices, smallest centrality vertices, then you're able to find the root for preferential attachment. So f of k is equal to k. You need 1 over epsilon squared. for, okay, I think now I'm out of time. So I just want to highlight that you have very sensitive dependence on the actual properties of the function f itself. So if you have a preferential attachment plus beta, then the amount of budget that you need sort of changes. It depends on that beta, etc. So once again, showing the effect of the initial seed in some sense, sort of long range dependence. Okay, so I'm going to skip. I just want to say, so this is just the tip of the iceberg in the sense the centroid centrality is not it works only for trees. There are huge open problems. Suppose you want to do similar sorts of problems for networks instead of trees. What can you do, etc. So there are lots and lots of open problems. One could try degree-based centrality measures, which only work in some cases. They don't work in other cases, etc. So, but the basic punchline is there are lots of interesting problems here, completely open, wide, I think, hopefully of relevance for lots of our audience. And many of these results, at least now, seem to weirdly depend on continuous time branching processes. Okay, that's it. That's my talk.
Okay, thanks, Shankar. We have time for a few quick questions. Yes, Das?
Yes, hi, Shankar. Thank you very much. I was wondering, in the change point problem, you talked about how there is this long-range dependence for any value of gamma. But suppose that you were to take a much smaller time, say log n, would you be able to identify such a kind of time where there is no more any long-range dependence?
No, very, very good question. So, so first off, this so-called quick Big Bang tries to do something like this, where we do n to the power gamma, but the same proof techniques, can be used essentially to say it doesn't matter how slowly as long as things are actually, sort of backing up and saying something maybe a bit deeper. So, and related to Professor Massoulié's talk, suppose you have two preferential attachment models, and they grow up to size 10 identically. Okay, so they have the same structure up to time 10. So until they grow of size 10 vertices, let's say. But after time 10, they evolve independently using the same attachment function, but completely independently. Then this effect of this initial 10 can in some sense still be recovered if you observe these two correlated networks after a long period in time. So not just n to the gamma, or as your nice question, log n, even if it's of some size k in principle, and not with probability going to 1, but with some non-trivial probability, there will be correlation between these two graphs. So the initial seed is always, the effect of it is always present in some sense. Does that vaguely answer your question?
Yeah, thanks. That's great.
Thank you. Any other questions? Okay, I had a quick question about your centrality measures. I wondered if you had looked at the work of Shah and Zaman on rumor centrality that was based on an SI model.
Yeah, great question. Yeah, so this area, I'm super excited about this. I mean, for the community, I think, not necessarily only for me, but for the community, I'm super excited about these finding the initial seed, because there are tons of open questions. In particular, you could ask, so what we established were, for a particular centrality measure, we established necessary and sufficient bounds. So you could ask, can you establish lower bounds? So given an epsilon, can you say that any root finding algorithm needs at least so many, a budget of so much size? And can you understand its dependence on epsilon? Now, the Shah-Zaman paper, so it's this rumor centrality, it's related to some notion of likelihood. So trying to estimate this attachment function f based on, or it can be converted to something like this. So what is conjectured, or maybe not conjectured, I should not say conjectured, what I think is one can hopefully use their sort of centrality measures or these maximum likelihood-based centrality type measures to obtain lower bounds for such algorithms. But we thought a little bit about it, but we couldn't make much progress. But yeah, that would be a fascinating direction to use those sort of centrality measures, to use that centrality measure, sorry.
Thank you. Any other questions? Okay, if not, let's thank Shankar again for a very interesting talk.
Hey, thank you.